I see that. You'll remember yesterday what the deal was. We went through the Newton's 3 laws kind of in a general, kind of broad sense. Sort of gave you that grade 10 review, I guess you could say. And then today we're going to look at each one, over the next 3 days, we're going to look at each one individually. Okay? Cool? It's my turn. We got a nice little chat. Lunch is over. 1:13. Time to go. 1:14. Yeah. So just a reminder, Newton's first law says if there's no force acting on a body, it will continue in its state of rest or will continue moving along a straight line with uniform speed. And I'll give you another quick little sort of the translation to that, right? Objects at rest, stay at rest. Objects in motion, stay in motion. Unless there's an outside force, right? Unless there's a force. Okay. So most people, as I said yesterday, most people can sort of regurgitate that back or memorize that little statement, but they don't really either A, believe it, or B, understand what it really truly means in sort of everyday world.
Okay, so let's say you roll a ball down a hill, and then it starts rolling down the hill, it becomes speed, and it gets on the flat ground.
Yeah.
Like, it doesn't just keep rolling.
You're right, it doesn't.
What's acting on gravity?
No.
Friction.
Right? Objects in motion stay in motion unless there's an outside force, and 99.9% of the time there is an outside force and there's no friction. And that's where the problem lies, actually, is that people don't they view it as the other way, right? Objects always slow down unless you keep moving them, keep pushing them, right? But that's not exactly the case. So today's lesson is simply to challenge you on that thought. So what I've done is I've created, how many questions are they handed there? Like 11 or so? 10. 10 or 11? 13. Okay, 13. Okay, so we're going to do it this way. I'm going to give you about 13, 14, 15 minutes to go through those questions. You can talk amongst with a partner kind of thing if you want. Answer your clicker, and then I'll go back to number 1, and we'll see how you did, and I'll sort of try to change your mind on a few things. Okay? So, you can go ahead and start that. Overall, we scored 57%. 57%. Okay, so now what we're going to do is we're going to go through them one by one, and we'll sort of see where we went wrong and try to figure this out. Okay, so Jay, I need you to put that away, and I need you to listen. Okay? Teach the partners. Okay, so question number 1 says, imagine a place in the cosmos out in outer space far, far away from all gravitational and frictional influences, so you're like a long ways away from planets or anything like that. Suppose that you visit that place, not magic school bus, I'm not sending anyone there, and you throw a rock. The rock will A, gradually stop, or B, continue in motion in the same direction at constant speed. The answer is B. Objects in motion stay in motion. There is no gravity. There's no friction. What's that?
I didn't read the cosmos.
I suggest you read more. That's kind of a warm-up question. Question number 2. A 2-kilogram object is moving horizontally with a speed of 4 meters per second. Okay, cool. Do you understand that I'm doing some teaching here? 2-kilogram object moving horizontally with a speed of 4 meters per second. How much net force, total force, is required to keep the object moving at this speed and in this direction? I don't want a decimal place, just give me the number. And the number, correct one is? 0.
You're what?
0 newtons.
Why?
Because objects in motion stay in motion.
But they're not in space.
Doesn't matter. That's true here on Earth too, right? It says how much net force is required.
What is that?
The key word is net force, total force. So if you've got a 2-kilogram object and it's moving like this, and let's say that there's friction of minus 10, how much do you have to push? 10. You have to apply a force of 10. But the net force, the overall force is
Zero.
zero.
What? Wow.
You should really get that to your body. So you can hear me. Okay? The net force is zero. This question, you're going to see it many, many times. This is the one I was telling you about yesterday. Just ask differently every time. Okay? The net force is zero. No force is required to keep it moving.
Net force always zero.
If it's moving at a constant speed,
Makes sense.
AJ, that looks to me like you're listening to something.
Oh, thinking.
Yeah, I see it. It just looks to me like you're doing the old, well, I'm going to hold it close to my ear, splitting hairs. All right, number 3. Mac and Tosh are arguing in the cafeteria. Mac says that if he flings the jello with greater speed, it will have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. Who do you agree with? Explain why. And the answer is, pretty much evenly spaced. The answer is Tosh. It does not. Tosh does not depend upon speed, or inertia does not depend upon speed, rather upon mass. Bigger objects, like filing cabinets, are harder, A, to get going, and they're also harder to be stopped from moving. Okay? What you're thinking about is momentum, and that's a grade 12 concept. Something we haven't talked about yet. You're thinking about momentum. Okay? Okay, I'm really trying hard to let you hang on to that because I know you need others. I see that, right? And I'm really trying hard. And then Zane starts talking about you got a shot.
No, I'm just saying, that's, if you chuck a baseball like this, or chuck a baseball like that, you're just giving an example. Like, I'm just saying,
Come on.
Okay, so then share for all of us.
well, I'm just saying, if you throw like a baseball, it's like gently underhand.
Yeah.
You're not throwing it very hard, so it's inertia would be small. But if you like
Really lay into it, yeah?
really would just hammer it like that thing's going to be harder to stop.
Yeah?
So I could throw this underhand and just bounce off. But if I like really whip it, it'd be harder to stop.
But that's momentum, not inertia.
But I thought inertia was.
No, inertia is not a numerical value. It's the quantity or it's the quality, property of an object to want to keep moving or to stay stopped.
But if you throw a baseball really hard or a rugby ball really hard, you're going to want to keep going. It's not going to want to stop. You can just same thing you said about the filing cabinet. Once you get it going, it's harder to stop. If you throw a filing cabinet really, really fast, it's going to be a lot harder to stop.
That's momentum. It's momentum.
Yeah, then
Sorry, man.
why did you say the filing cabinet? So inertia is.
Let me think about a better way to explain it. I'll come back. Okay. Let me percolate that in the back of my brain while I'm doing something.
Let's review what your inertia is.
Yeah. Okay. Let me think about that. Suppose you're in space in a weightless environment. Would it require force to set an object in motion?
Yes.
Yeah? The answer is yes. Everyone got it right.
Yay!
Awesome. How come in space you need a force to get something to move?
Because
Because an object rests. If I'm out in space and I'm holding my little roll of tape and I just let go, what does it do?
it just
It just stays there, right?
You do that here, it falls.
Well, that's true. But if I sort of leave it like this, right, it just stays, right? A force is required to set an object in motion. Okay. Fred spends most Sunday afternoons at rest on the sofa watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? Well, it increases his inertia.
Yay!
Makes him bigger. Still thinking.
I said.
Still thinking.
And what about if he plays rugby all week and on the weekends he...
Then it might balance. It might balance. Yeah.
So
You would have to include that as part of this to have the C, right? Yeah. Fair enough.
what do you do, Leo?
Okay. Been too close. There's a lot of reading here. Been too close is being chased through the woods by a bull moose which he was attempting to photograph. The enormous mass of the moose is intimidating. but if Ben makes a zigzag pattern through the woods, he'll be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. Is it the moose has more mass, so he has less inertia, so he's not able to make zigzags as easy? Is it the moose has more mass, so he has more inertia, so he's not able to make zigzags as easy? Or is it will not work, the moose is still able to make a zigzag pattern?
B.
I hear B. And the answer is indeed B. The more mass, the more inertia, not able to zigzag. You will see
Oh, I read that so wrong.
the little running backs. I don't know what they call them in rugby, the guys that are running the ball mostly. Okay, the backs. You will see them generally being smaller, and they're able to go left and right, right? The bigger guys, the linemen in football, the forwards are generally the larger players,
Big balls.
right? And they aren't able to go left to right.
Unless
How
they
come?
bring pumps up.
They got bigger mass.
So,
Yeah. The Titanic. You all know the story about the Titanic? Iceberg ahead. Did they try to get out of the way? They did, but the Titanic was literally Titanic, huge, right? Big, big mass. To be able to move that quickly, you need big, big force. Not enough force to be able to move sideways faster. Ran out of time.
Didn't it hit like the side of it though?
Yeah, it was like, it didn't miss by much.
what happened? They should have just went head on and tried to crack it.
Yeah, I know, that's what I should just try to go head on.
Yeah, that would have been horrible. So much worse. So many more people would die. So it's been like, no chances for going. I don't know what we're talking
They
about.
should have slapped it in reverse real quick. Wait, what?
Yeah, that's always good for the gearbox, just slam it in reverse.
Well, I mean,
Well, I think it's better
it
than.
would have been better than killing everyone.
Yeah?
Can we figure out?
Okay, so let me ask you this. If it had immediately slammed in reverse, what would have happened to everything on the Titanic? Right to the front, right out, like,
Like, you
exactly.
know what I mean? They should have put it in reverse and then like started trying to like selling it flat out and see the things in reverse.
Oh,
That's
okay.
how it's slowing down.
Flies into the iceberg.
Both safe, people dead.
Yeah. Save the boat.
Anyway, there's
Okay. Oh, more reading for me. Two bricks are resting on the edge of a lab table. Surely she's short, stands on her toes and spots the two bricks. She inquires an intense desire to know which of the two bricks are most massive, which are bigger. Since Shirley is vertically challenged, she is unable to reach high enough and lift the bricks. She can, however, reach high enough to give the bricks a push. Discuss how the process of pushing the bricks will allow Shirley to determine which of the two bricks is most massive. What difference will Shirley observe, and how can this observation lead to the necessary conclusions? So, is it the brick that moves more has more inertia and is heavier? Is it the brick that moves more has less inertia and is lighter? Or is it both bricks feel the same and move the same distance? And you probably, I'm hoping, got this right. B. Things that move more are lighter, right?
therefore.
How she,
Have less inertia.
how she can,
She can just reach up and push. That's all she can do.
yeah, but.
How can she see?
Why not?
Yeah, I don't know. She climbs on a ladder later. No one ever asked me that. Okay, here's where the argument starts. That is one fat cat. By the way, this is a fictional story. No actual cat was carved in the making of this question.
Okay, I was ready for that.
Okay? Alright, here's where the argument starts. Look out below drops an approximately 5 kilogram fat cat with a weight of approximately 50 newtons off the roof of his house into the swimming pool below. Upon encountering the pool, the cat encounters a 50 newton upward resistant force, assumed to be constant. Use this description to answer the following three questions. Are the three of them? I think, right? Which one of the velocity time graphs, so as soon as you're talking graph, immediately try and identify what kind of graph it is. So these are velocity time graphs. Best describe the motion of the cat. Support your answer with sound reasoning. So, which one of these is correct? And the answer is B. How did we do?
Oh man, good.
The answer is B.
Why?
Why is it B? Okay. So as the cat falls, I'll use my tennis ball as my cat. As the cat falls from the roof, I heard Zane say it, the cat picks up speed, right? Goes faster and faster and faster, but it's going down, so that speed is negative. And then once it hits the water, you got 50 newtons down, you got 50 newtons up, right? Which makes the net force 0, which means that it no longer speeds up. But it still keeps going, because it says that in the question.
Like what is making that?
The water is applying a frictional force,
Okay.
right? Now, most people say, oh, I've dropped cats in pools before. They don't want to say that. No, I've dropped things in pools before, and it slows down. And I go, fine, this isn't that case. It tells you what the numbers are. It says that there's 50, Olivia's really worried about this cat, I can tell. No cats were harmed, it's just a picture, Olivia. Just a story. Cat's fine.
So he's saying that you go to the bottom of the pool.
Yeah, at a constant speed, right? As the cat is falling, how much force is pulling on the cat? 50 newtons. When it gets to the water, still 50 newtons down, gravity. But now the water is pushing up a point force of 50 newtons, which makes the net force 0. And if the net force is 0, all it does is stop speeding up. And so the graph becomes flat.
But what if it was a rock?
Doesn't matter what it is.
He's saying,
Doesn't matter what it is. Right? As long as the forces are balanced, Leo, it doesn't mean that it slows down. It just means that it's not accelerating anymore, not speeding up anymore. So you're getting hung up on what you see in real life.
this is
Right.
a real life one.
Well, normally in real life, the force up would be 40, more than 50, and the cat would slow down. Right? The cat would slow down. You all jumped into pools before. You know when you hit the water,
He's saying,
well, you sink, but you slow your speed down, right?
Like last week,
Put it
less than 50 then.
Yeah. No, but to slow you down would have to be more force up. Right? If it was less, you would just
Keep on going.
boom.
Well, but we do keep on going.
You keep on going, but you're not going as fast. Right?
Okay.
Yeah. I know it's a hard. Kids have a tough time with it. Okay, so which one of these graphs? Now, if you got the last question wrong, you're likely going to get this one wrong, right? Which one of the following dot diagrams best describes the motion of the falling cat from the time that they're dropped to the time they hit the bottom of the pool? The arrow is where they hit the water. So because they're speeding up, the dots are farther apart, and then once they hit the water, the diagram, the dots should be the same distance apart, and so the answer is A.
Start to speed up.
Yeah, see how the dots are getting farther and farther apart? And then once they hit the water, same speed. What's happening in B?
You're kind of slowing down.
Yeah, falling at a constant rate and then slowing down. This one is speeding up and then slowing down,
Okay, good.
right?
Shouldn't there be an extra darker dot at the bottom of A showing that it's stopped?
I suppose.
Down to the.
Oh, yeah, I guess we stopped recording as soon as the cat got there. Yeah, good point.
C would be like real life.
C would probably be a little bit more realistic, right? But in this case, the forces are balanced.
I put B because I was like seeing
Well, I was
from the bottom to the top.
Okay. Several of Luke's friends were watching the motion of the falling cat and laughing at the poor cat. Bad boys. Don't do that. Being physics types, they began discussing the motion, and who hasn't done that at home, discussing physics with your friends?
All the time.
Yeah, all the time. Discussing the motion, made the following comments, indicate whether each of the comments are correct or incorrect. Support your answer. Once the cat hits the water, the forces are balanced, and the cat will stop.
Boss.
False. False. Is part of that true? This part is true, right? Are the forces balanced? Yes, that part is true. Upon hitting the water, the cat will accelerate upwards because the water applies an upward force. False. There is no acceleration because the net force is 0. False, because the forces are balanced. The net force is 0. The A is 0. The cat speed stops changing. It still keeps falling at the same rate. Again, this is because those forces are equal, right? Which may or may not happen in real life. So the answer again is false. Upon hitting the water, the cat will bounce upwards due to the upwards force. False. False, false, false. Again, forces are balanced. Acceleration is 0. And the last one. Okay. If there's anything you learned today, this is the one you got to know. Because this is the big daddy of them all, Brandon. If the forces acting upon an object are balanced, the object, and I'm waiting for a drum roll, the answer is C, which hardly anyone took. Let me explain. If the force is acting upon an object balanced, the object must not be moving. So all you listening, because here's the number one thing to learn today. Right? Must not be moving. Can you give me an example where forces could be balanced and the object continues to move?
A rock and rugby. We just did,
I don't know what that means.
You would not just.
a rock. Oh, okay, I know, Jack, in the pool. Okay.
I feel like, I don't feel like this is, I'm not doing that. That's not like,
I'm already on the ground for adult enough.
well, then just pretend someone already on the ground.
You know what? Yeah, you get up.
I'm glad that you guys do. I don't feel
So
like.
bro got tackled down here, buddy got tackled, right?
Yeah?
Brandon's protecting him. I'm trying to get through.
Yeah.
Say that we're both like the same strength.
Uh-huh. So you're both pushing with the same force.
Yeah.
But I asked for an example where you are still moving.
But we're balanced.
Okay, so that would be
And we're still trying
that
to
would
move
be
each
the
other.
example I want when I get to peak.
Okay,
Right?
no,
So, okay, that's fine. We'll do this.
We thought we were geniuses.
Yeah, if the force is acting upon an object of balance, then the object must be moving at a constant velocity. No, that one can't be true, because if the forces are balanced, like the guys demonstrated, they would be at rest. But does it have to be not moving? Does it have to be at rest? No, in fact, Brett is right. We just did that one. This cat does what? Keeps moving at a constant speed because the forces are balanced. I'll give you another example.
So that's, that makes sense. I got it.
Right? Another example would be when you're driving down the highway. Is there air resistance?
Yes.
A lot. Do you need a force to keep moving?
Yep.
Yes. If you got it on cruise, if you got 1,000 newtons of air resistance, how much force do you have in your engine pushing forward?
More than that.
The same amount, 1,000. Moving at a constant speed. Right? Don't need more. If you had more, you could use enough, exactly. Cole, do you think maybe you could have waited to do that thing? You think maybe?
I didn't hear that.
Oh, I know, but it was a little distracting. You think you could have waited till I was done? That's my point. I think you know the answer. Okay. Remember yesterday when I did that amazing tablecloth trick?
Is this one where they try to
Oh, yeah, we got stories.
Yeah?
Oh, that thing yesterday?